Hi everyone, welcome back to Pair this line. Today we are going to work on a great project. We want to build like a coat of a Stanford bunny mesh. What does it mean? To add thickness. So to do so, we need first to compute the bounding box of the Stanford bunny mesh. Then we need to compute the grid mesh. So we need to divide in voxel size and to get the grid from the bounding box and also to add some padding. Then we want to compute the distance from each single point in the grid to the mesh surface. To do so, we need to use the sign distance function, SDF function, and this function will provide to us two things: the distance from each single point from the grid to the surface, and also 0 or 1 or minus or positive number or negative number if we are inside the mesh or outside the mesh. It's also called as occupancy. So we need to compute the distance and also the occupancy. Then we will be able to select the points of the thickness, okay, meaning in a certain distance to the original surface of the Stanford bunny mesh, and then to build matching cube from this area from all the points that will be inside this new area, and to be able after that to do some erosion to get the mesh reconstructed. So let's do that together now. It's a great project. Okay, so to do so, we need to import as usual NumPy as NP, Open3D as O3D, Loguru, import logger, and some also custom functions that I wrote in another module. Let's do in debug mode, and let's start it. Okay, pipeline config is also is only to have our parameters, so voxel size, padding voxels, shell thickness, erosion, iteration, and color map. So the voxel size to divide to get the grid mesh, okay, the mesh grid, sorry. Padding voxel is to make the bounding box bigger in order to get more points and more padding. Shell thickness is to select the millimeter. So in this case, it's 1 millimeter. Erosion iteration is meaning when we are going to use binary erosion to reduce, and we will see another impact than last week. So this is number of iteration, and the color map is only to visualize the SDF function. So this is the parameters. You can change it as you want. The first thing to do is to load the mesh. So if you don't put some pass, so it will load the bunny mesh. If you add a pass, it will load your mesh. Okay, let's visualize it. Okay, after computing the vertex normal, so good visualization. Okay, then we want now to create the voxel grid. Okay. Okay, so to create the voxel grid, I want to go inside. So first, I'm computing the get axis aligned bounding box. Then I'm declaring the padding, which is the padding voxels times the voxel size. I compute the min bound and the max bound, and I generate grid vectors, the X, the Y, and the Z. I just add here this thing to avoiding divided by 0. Grid shape is the length of each single one. So we can see the dimension is 36, 36, 33. And the grid X, grid Y, and grid Z is equal to np.meshGrid of this one, indexing ij. And then we just concatenate in the horizontal side and also the transpose. So we get now the points of the grid shape, and the mean bound. Now we are going to use compute SDF Open3D. So we want now to compute to have the distance from each single point of this new grid. So we need to put the argument the original surface of Stanford bunny mesh, and the points of the grid. Let's see inside the function. So we compute legacy. It's another structure of 3D mesh in Open3D to compute RaycastingScene and then compute the surface, the sign distance function. So let's do it. query point tensor, and then sign distance is equal to query point tensor when the query point tensor are in fact the points of the grid. Okay, so then we compute the sign distance. Now we can see that here we have only, okay, this is the number of points in the grid, if you remember, and now we have inside all the distance. So it will be only one float, 32, for a distance for each single point. Let's continue. We just reshape it to the grid shape, okay? To have, in fact, the distance in the same shape of the grid shape. And then we want to create the grid with now the distance with a color adapted to the distance from each point. In other terms, we want to have like a gradient of color adapted to the distance from the original mesh surface to the padding bounding box. So let's see that. Create color point cloud. We can go inside. So we are going to use matplotlib for the color map. We get the np.abs, so absolute of the SDS values, because the SDS values are negative inside and positive outside. So we get absolute to get a gradient from the original from 0 to the outside. We just normalize it. And then we get the color. So by default, the CM of matplotlib is providing RGBA. So we just remove the A and we keep RGB only. And then we just assign the points to the pc.points to a new object of point cloud and the color to the pc.colors. So with the distance, the color adapted to the distance. So let's visualize it. Okay. So now this is our grid. And we can also click on plus, okay? And this is a great grid with a distance. You see when it's yellow, the distance is very far, and when it's more blue, the distance is close. And we can also go inside the mesh and we see other points with blue color. Let's continue. Now we compute occupancy open 3D. We want to know if it's occupancy, meaning if it's inside the mesh or outside the mesh, and to get 0 or 1 accordingly. Let's go. So recasting mesh. So the same logical, we just did it. And occupancy now providing, let's see what is occupancy exactly. Yeah, occupancy is only 0 or 1. You see the max is 1 and the min is 0, and the same number of grid points. Now the selected mask. I want to select the mask. What does it mean? I want to select the coat of the bunny mesh. So to select the coat, I'm first using the outside shell. So when the SDF value is superior to 0, meaning we are outside the bunny mesh, and also the SDF values are less than the shell thickness, meaning 0.05, I think. This is the first parameter. And the second one is the occupancy. If the occupancy, meaning if it's 1, the occupancy is 1, meaning we are inside the mesh, or it's outside shell, this is this parameter. So then I select the mask. So meaning it will select all the point inside the mesh and also the point outside when it's less than the shell thickness. Return selected. And then we can assign this selected point to a new point cloud and to assign also the colors as well. And then we can visualize it. As you can see, so it's great. We can see the full bunny mesh, okay, with the points from the grid. And you don't see that here, but it's bigger than the original one. We will see that in a few. And here, because it was not closed completely in the bottom, so we have it out layers, but it will be also removed by the erosion. So let's continue. Then I want to now, after selecting match, to get the volume binary volume and the volume eroded, because it's the same logic as last week. So generate binary structure, binary erosion. Now we want to see the impact of the erosion when we work with a marching cube. So we reconstruct the mesh from binary. Okay, so let's reconstruct the mesh using marching cube. Marching cube is a great method when we have a full point cloud, as we just seen. It's like a volume, a full volume. So we can compute a mesh using marching cubes. from scikit-image, and we are going to see the result. Then we just color it, and then we now compute that from the eroded points. Okay, this is the result after erosion. And we can see inside it, we will see the other mesh. Okay, we don't see. Okay, we will see in the next one. Yeah, in this one, sorry. Okay, we see. This is the first one. This is the coat of this one. We're going to visualize it using MeshLab also as well. And then you can just save the eroded, the mesh original, and the mesh reconstructed before erosion. And this is pipeline complete. So let's see now this one. Okay, so this is the first reconstruction before erosion. Let's see the difference between this one and the original one. Original one is this. Let's make it transparent so you can see it's great because we see a big coat, okay, with some outliers. Let's see the impact of that after doing, let's remove the original and just work with the eroded one. You see the eroded one after computing the erosion, it's even less, it's even smaller than the big one, than the original big one. And when we compare to, we remove this one and we compare to the mesh original, so we have the code of this one in mesh. Okay, so that's it for today. It's for me, it was a great project. I hope it was the same for you. And so several things. Next week we're going also to see deeper in theory. And please subscribe to the channel and share it. And let's go ahead together. Thank you.